Alright, in this video we're going to be looking at the Poisson distribution. So just like your binomial distribution as well as your geometric distribution, the Poisson distribution is a discrete distribution. So it means that it takes exact values. And the Poisson distribution is used to measure the number of events that occur within a given time or space. And there are four conditions that must be met for a Poisson distribution to be a suitable model. So those conditions are as follows. Events must occur randomly. This is the first condition. The second, events must occur singly. The third, events must occur independently. And the fourth, events must occur at a constant average rate. Alright, so if these four conditions are met, then a Poisson distribution is a suitable model. And the notation we use for a Poisson distribution is X follows a Poisson distribution with mean lambda. So this lambda here, our parameter, represents our mean. And note that under a Poisson distribution, mean is the same as variance. So it means our lambda is both mean and variance. Alright? So to calculate our Poisson probabilities, we use the formula. The probability that x is equal to r is equal to e to the negative lambda times lambda to the r over r factorial. This is your formula for Poisson probabilities. So now let's get our hands dirty. Let's do some past paper questions on the Poisson distribution and Poisson probabilities. So the first question that we have here says, customers arrive at a shop at a constant average rate of 2.3 per minute. Part A, state another condition for the number of customers arriving per minute to have a Poisson distribution. So we say the four conditions that have to be met for a Poisson model to be suitable. So in this case, they're saying customers arrive at a shop at a constant average rate. So the condition for events happening at a constant average rate has already been met. The other conditions that we could mention for our answer are that customers arrive at the shop randomly. Randomly could be one answer. Randomly. Or we could also say that customers arrive singly. Or we could also say that customers arrive independently. Any one of these would do for a solution. Alright, it is now given that the number of customers arriving per minute has the distribution Poisson with lambda 2.3. Find the probability that exactly 3 customers arrive during a 1 minute period. So let's say x is the random variable, number of customers arriving per minute. So x follows a Poisson distribution with lambda 2.3. And we're required to find the probability that 3 customers arrive, so x equals 3. So using our formula for Poisson probabilities, that's e to the negative lambda, so 2.3, multiplied by lambda to the r over r factorial. So let's punch this into our calculator. That's e to the negative 2.3 multiplied by 2.3 cubed over 3 factorial, and this gives us 0.203, and that would be our final answer. Now part C says find the probability that more than 3 customers arrive during a 2-minute period. So notice the change in interval. In part B, and even in the stem of the question here, we're dealing with a 1 minute period, but now they've changed it to a 2-minute period. So let's redefine our random variable and say let y be the RV, number of customers arriving. They're no longer arriving per minute, it's now per 2 minutes, because they've changed the interval there, per 2 minutes. So it means y follows a Poisson distribution, but our lambda now, if the customers are arriving at a constant average rate of 2.3 per minute, what about per 2 minutes? That means that's 2.3 times 2, since we're now doing per 2 minutes. So 2.3 times 2. So when your interval changes, your lambda is also going to change with your interval as well. So this becomes y follows a Poisson distribution, 2.3 times 2, that gives us 4.6. And we are evaluating, find the probability that more than 3 customers, so greater than 3. So probability that y is greater than 3, we can write this as 1 minus the probability that y is less than or equal to 3. So that becomes 1 minus, then we have to evaluate each probability. So y equals 3 is going to be e to the negative 4.6 multiplied by 4.6 to the power 3 over 3 factorial plus e to the negative 4.6 times 4.6 squared over 2 factorial plus e to the negative 4.6 multiplied by 4.6 plus e to the negative 4.6. That's 40. Alright, now alternatively, instead of writing this whole expression, you could have factored out e to the negative lambda, so this would have been 1 minus e to the negative 4.6, then it becomes 4.6 cubed over 3 factorial plus 4.6 squared over 2 factorial plus 4.6 for this term here, and then plus 1 for this term. And this is the typical convention that you will see in evaluating Poisson probabilities for inequalities. Alright, so let's evaluate that using our calculator. That's 1 minus e to the negative 4.6 multiplied by 4.6 to the power 3 over 3 factorial plus 4.6 squared over 2 factorial plus 4.6 plus 1, and this gives us 0.674, and that's our final answer. Let's look at another example. Here we're given that the number of accidents on a certain road has a Poisson distribution with mean 0.4 per 50-day period. Part A, find the probability that there will be fewer than 3 accidents during a year. Alright, so let's define our random variable x. Let x be RV, number of accidents per year, or per 365 days to be more precise. So per 365 days. X follows a Poisson distribution. What's our lambda? Here we're given that the mean is 0.4 per 50 days. We've got 365 days, so that would be 365 over 50 multiplied by 0.4. There's a change in the unit interval. So 365 over 50 multiplied by 0.4, that gives us 2.92. So lambda here is 2.92. And we want to find the probability that there will be fewer than 3. So probability that x is less than 3. And so this is the probability that x is equal to 2, 1, and 0. So that's e to the negative 2.92. Then we've got 2.92 squared over 2 factorial for x is 2. Then 2.92 for x is 1, then 1 for x is 0. So let's punch this into the calculator. This is e to the negative 2.92 times 2.92 squared over 2 factorial plus 2.92 plus 1, and this gives us 0.441, and that's our final answer. Now in part B, we're told that the probability that there will be no accidents during a period of n days is greater than 0.95. Find the largest value of n. Alright, so let's define our random variable. Let y be RV, number of accidents per n days, so per n days, and y follows a Poisson distribution with lambda. So to get lambda for 365 days, we say 365 over 50 by 0.4. So this means that to get lambda for n days, it's going to be n over 50 by 0.4. And this here simplifies to, we've got n times 0.4 over 50. So that's 0.008 n. That's going to be our lambda here. And we're told that the probability that there will be no accidents, so if there are no accidents, it means that y is equal to 0, right? The event does not happen, y is equal to 0, is greater than 0.95. So this probability is greater than 0.95. Okay, find the largest value of n. Alright, so let's use our formula for Poisson probabilities. If one probability that y is equal to 0, that's going to be e to the negative 0.008 n. Alright, and this is greater than 0.95. And so if we want to solve for n here, we're going to have to apply the natural logarithm on both sides. Ln, so we get negative 0.008 n is greater than ln 0.95. Alright, so here we're going to divide both sides by negative 0.08 n, and remember, if you've got an inequality and you divide by a negative number, the sign changes direction. So this becomes ln 0.95 divided by negative 0.008. So n is less than, let's punch this into the calculator, that's ln 0.95 over negative 0.008, and this gives us 6.41166 and so on. Okay, and what do they want? They want the largest possible value of n. So n represents the number of days, so n must be an integer. So the largest integer that is less than 6.4 is going to be 6. So we can say that n is equal to 6, or largest n is 6, and this will be our final answer.